So we have been studying partial differential equations. We looked at some very general aspects and how to classify partial differential equations using the discriminant of the quadratic form involved. So in this lecture, we will look at a specific PDE, which is of great importance in physics. It finds applications in a number of fields in physics and engineering. And so we will, start with some very elementary properties of this differential equation, and then we will describe how to solve this equation in the following lectures. Okay, so the Laplace equation has this Laplacian operator del squared, and it acts on some function which can be a function of one variable, two variables, three variables, or even more sometimes, but usually we restrict our attention to two variables or three variables in x, y, and z is as far as we go in physics. Right? It's of the elliptic type, right? According to the classification we have seen. So elliptic type comes about when dou squared u by dou x squared and dou squared u by dou y squared, both of them have the same coefficients, same sign, same magnitude, same which is just 1 in this case. And so it appears in actually it's a number of contexts. So like we said, so heat conduction is one of them. Then also you might have encountered this in the context of electrostatics, electrodynamics. Magnetic potentials can be described using this differential equation. So yeah, one concrete example is that of temperature fields, right? So if you have a heat rod which has reached steady state, and so often we're interested in finding out the temperature profile of a heat rod or some object with some specific geometric shape. That's where many of the details of solving this kind of a PDE will come in, depending upon the geometry and the boundary conditions, and also those things will come a bit later. So the point is that it's a kind of a dynamic equilibrium is set up where the amount of heat flowing into some region is equal to the amount of heat flowing out of it. Therefore, the temperature at any point in space is going to be a constant as a function of time, and so that's going to be described by this Laplace equation, right? So if you're in 2D or if you're in 3D, it's a little more complicated. So what we will do is we will start with the one-dimensional version of the Laplace equation, which is in fact kind of a trivial differential equation. It's not even a partial differential equation. It's just a function of a single variable. So we might as well write it as d squared by dx squared acting on u of x equal to 0. So if you integrate it once, you get du by dx is equal to a constant, and then if you integrate it a second time, you'll get c1x plus c2, where c1 and c2 are constants which are available for you to fix based on boundary conditions. Now, so yeah, so the solution is a straight line, and so already there is there's insight which we can pull out from just the 1D version, and which we will see will carry to higher dimensions as well. So the key point is that the this equation is explicitly a tendency to iron out all curvature, right? So the second derivative is where the information about the curvature of the function is contained. So we know that du by dx is the slope, d squared u by dx squared is the curvature. So clearly the solution does not contain any quadratic part to it. It's a straight line, right? So there's another way to think of this feature. I mean, a straight line means that basically there are no maxima or minima sitting in in the bulk, right? So you can, of course, there is at the edges, of course, right at the top of the line and at the bottom of the line, it's going to be the maximum and the minimum, right, are possible at the edges, but within the center there is no curvature, right? So the line is not allowed to bend, right, which is in some sense explicitly forbidden by this condition, and therefore it's a it's going to give you no maxima or minima, right? So another way of thinking about this is that in fact the value of this function at any point is going to be the mean of the value of the function in its neighborhood, right? So if you're sitting on a straight line, so clearly the value of the function at any point is going to be the average of the value of the function slightly above and slightly below, right? So I mean, if you take the same distance above and same distance below, you can average it, right? So there is a more rigorous way of stating this, and so we will see this as we go along. I mean, we will state it in a more general fashion, perhaps not with complete rigor, but it is possible to state this property, and it's in some sense these two properties are closely related. One is the fact that there is no curvature, which means that you cannot have maxima or minima, and so that also is in some sense equivalent to the fact that you have this mean value property, right? So this, it turns out, actually carries forward to higher dimensions as well. So in 2 dimensions we will revisit the same couple of properties a little bit ahead in this lecture. But I mean, it's also useful to point out at this point that in fact we have already encountered functions which satisfy the Laplace equation. Functions of 2 variables which satisfy the Laplace equation we have already encountered, right? So these are the real and the complex parts of analytic functions, right? So we have seen that analytic functions are made up of 2 functions of 2 real variables. So there's the real part, which we are often called u of x comma y, and then there is the imaginary part which we call v of x comma y. And each of these, the Cauchy-Riemann conditions must hold if these the overall function is analytic, and therefore individually you can show that dou squared u by dou x squared plus dou squared u by dou y squared equals 0, and some similar equation also holds for the imaginary part. So harmonic functions, right, functions which satisfy the Laplace equation are called harmonic functions. We have seen that analytic functions, the real and imaginary parts, both are separately harmonic functions. So now harmonic functions, like we just said earlier with the 1D case, satisfy these 2 crucial properties. One of them is the value of the harmonic function at any point is the average of the values that the function takes in the neighborhood of that point, right? So let's understand this for the 2D version using a discretization of the differential equation. So you have this partial differential equation. So let's take this partial differential equation and then rewrite or recast it into a discrete version of the same PDE, where it becomes explicit how this average value property comes about, right? So the partial derivative is really u of x plus delta x comma y minus u of x comma y, the whole thing divided by delta x, in the limit of delta x becoming arbitrarily small, right? So if you're doing a numerical way of computing this, then you will make delta x small, but it's not going to go to 0, right? You can make it very small, but in practice it's going to be finite. And so you can either take the forward difference or the backward difference. Both of these are completely legitimate ways of working out the partial derivative of this function at the point x comma y, and in fact both of them have to converge to the same point, right? So that's how you have a meaningful definition of the partial derivative. Now if you go ahead and do a second derivative, right, so it's convenient to use the backward difference in the second one if you have used the forward difference in the first one, or backwards difference followed by forward difference, so that we get this nice form. So for example, if I look at the first expression here and then use the backwards difference to compute the second order derivative, then I will take this whole thing as it is. I'll just rewrite it here, minus u of x comma y minus u of x minus delta x comma y, the whole thing divided by delta x. Then the whole thing itself has to be divided by delta x. So that gives me a delta x squared in the denominator, and then there are these 2 u of x comma y's which come in. So I have a u of x plus delta x comma y minus 2 times u of x comma y plus u of x comma x minus delta x comma y. So this is a this is the discrete version of the partial second derivative with respect to x. We can also write a similar expression for the second order partial derivative of u with respect to y. So then we'll have u of x comma y plus delta y minus 2 times u of x comma y plus u of x comma y minus delta y, the whole thing divided by delta y the whole squared. So of course we intend to take the limit of delta x and delta y becoming arbitrarily small. Suppose we choose these two increments to be the same, delta, let me call this as delta, and then rewrite this the Laplace equation in terms of it's the sum of these two quantities. So if I write this discrete version, so I have this longer expression. So u of x plus delta comma y minus 2 times u of x comma y plus u of x minus delta comma y plus the whole thing again similarly u of x comma y plus delta minus 2 times u of x comma y plus u of x comma y minus delta. The whole thing has to be divided by delta squared, and if this has to be 0 because that's the Laplace equation. Now you can rearrange things and rewrite this as u of x comma y, right? So you can pull out, so if there's a minus 2 u of x comma y and a minus 2x comma y, you bring both of these to the left hand side and then divide by 4. Then you see that you get u of x plus delta comma y plus u of x minus delta comma y plus u of x comma y plus delta plus u of x comma y minus delta, the whole thing divided by 4. Basically what we are doing is we are looking at this function u of x comma y on a grid, right? Although the continuous version is where we started. So suppose we make a very fine grid of points. So what we have managed to show is the condition that del squared u equal to 0. So the Laplace equation condition is identical to saying that the value of this function u of x comma y at any grid point is equal to the average of the values which the function takes at all the neighboring points, right? So this property is in fact true even in the continuous version itself. You can come up with some way of writing an integral and show that the value of u of x comma y is going to be the average of the value that it takes in some neighborhood. You can come up with some path and then work it out and so on. There's a more rigorous way of showing this, but here we see explicitly and in a simple way that indeed there is this property of the mean value, of the function taking the mean value of its values in its neighborhood, and this is in fact identical to the property of of the definition of the Laplace equation, right? So this is completely equivalent to saying that you're solving for del squared u is equal to 0, and so this is in fact a way to solve the Laplace equation numerically, right? So in fact we will see exact solutions of the Laplace equation in 2D and maybe 3D as well. One can extrapolate some of these methods. So 2D is actually a great place to do. You can try and work this same kind of a property out for 3D and convince yourself that indeed you will have some kind of a cube and you will get the average of u of x comma y will turn out to be the average of all the nearest neighboring points in three-dimensional space as well, right? But so the key point I want to make here is that this is a way to numerically solve this PDE. So suppose you are given some complicated geometrical surface, right? And if you are given boundary conditions, you just make a grid and then put the value of the function u of x comma y to be 0 at all points, and then change the boundary conditions alone to the values that are given there. So if you have set the boundary conditions and then you just simply go to every point in your grid, make the grid as fine as you can, as fine as your numerical resources will allow you, and then simply keep on replacing every grid point's value by the average of its nearest neighbors. So initially, of course, there will be lots of zeros, so many of these updates will probably return 0, but slowly you will start seeing that the values from the boundary will start showing up in all the points of the grid, and there's going to be a point where when convergence is attained, you can actually match the analytical solution with the numerical solution, and you'll see that they will be basically the same, right? So this is in fact, it is a legitimate numerical technique to solve the Laplace equation. So yeah, you can think of a consequence of this is the next property, or you can also think of it in the other direction. Both are really equivalent to each other in some sense. So uh, the fact that every point's value is equal to the average of its nearest neighbors immediately implies that there is no chance that this function can have any maximum or minimum in the bulk, right? Because if it does have a maximum, that means that its value, if it is a maximum, for example, then the value of this function at that point is strictly greater than the value of the function in all its neighboring points. Therefore, the average of all of these is also going to be less than the value of this function at that point. So it cannot satisfy this property. So the fact that there is this mean value property is completely equivalent to the fact that this the harmonic function cannot have any maximum or minimum except at the boundaries, unless you have the trivial solution. If you have a trivial solution where the harmonic function is just simply a constant, that's the only case where you can have, then every point is a maximum or every point is a minimum, or that's a very sort of a special and trivial type of scenario. But in general, these two properties do hold for harmonic functions, and they are completely equivalent. That's all for this lecture. Thank you.